Air is a mixture of gases. Let's address that point first. If we take air, we can say quite clearly that it is a mixture of gases. I'm going to sort of introduce you to this idea a little bit, and we're going to analyze it a little bit too. Okay, so we've got a mixture of gases in air. The air in our outside environment that I'm breathing in right now, for example, I'm breathing out. We want to understand what it's made up of and how is it different when we breathe it in and when we breathe it out, and what are those components like. Now, if you step back from this and think about this from sort of an athletic performance perspective, we're going to discover, or maybe you know already, that oxygen, for example, is a reactant in the aerobic respiration process. So we know, for example, that oxygen is a reactant, effectively, it's one of the things that goes in, is a reactant of aerobic respiration. So it's going to be really important for performers to be able to consume, absorb into the body and then consume as much oxygen as is needed, or perhaps as is possible. But before we do that, let's subcategorize what we're going to do here. We are going to look at inhaled air. So just to be clear, so just all super clear, this is breathed in air, the air that goes from the outside environment into my lung. What are its components? And we're also going to look at exhaled air. Exhaled air, that's kind of hard to say, I don't know why. Exhaled air. And exhaled air is the air breathed out. All right, so this is what we're going to do in order to analyze this. First things first, let's bring our kind of circle tool into play here. And I'm going to draw as a big old circle for our inhaled air. And let's do the same for our exhaled air. It looks like they're kind of identical because, well, the quantity is going to be roughly the same. But what we are going to say here is that we're going to break this down. Now, the first thing I'm going to do is I'm going to try and identify the middle. So I'm going to sort of argue that the middle is there and the middle is there. I don't know if I've done it well. And let's bring our rule into play. I'm going to put this on here. And I'm first of all going to point this straight to kind of 12 o'clock, okay? And the first product I want to introduce, or the first gas from the mixture of gas I want to introduce you to, is nitrogen. Now, how much nitrogen do you reckon is in the air that we breathe in? What would your thinking be? And if your thinking is, James, well, I reckon I know. I reckon it is. Let's get rid of this. I reckon, James, I'm going to tell you that, oops, that wasn't what I meant to do. I'm going to tell you, James, that something along the lines of 78% of the air breathed in is nitrogen. Well, you would be correct, and good for you. Now, just be aware that some places you might see the figure 79, but we're going to report it as 78 here. It's sort of in between, so just be aware of that. So 78% of the air we breathe in, the biggest majority part, is nitrogen. Great. Okay, let's look at the next gas in our mixture, and I'm going to bring this all the way up here, and the next part, and I'm going to put it to, let's go to about there. The next part that we have, let's go here, let's go all the way down, let's go all the way up, and now let's actually fill that in there. This part here, we're going to say is 20% of the mixture of gases on the way in, and we are going to refer to this as oxygen. I'm going to put O2, molecular oxygen. By all means, write oxygen is absolutely fine. And we've now got the vast majority of the air we breathe in is made up of nitrogen and, of course, oxygen. Now, we've got this kind of 2% slither that's left. The only point I want to make about this, a real mixture of gases in there, but the point I want to make is that part of that, in fact, 0.4% of that, we've got 2% here, is a total 0.4% of that is carbon dioxide. Okay, so we breathe in a small proportion or a small quantity of carbon dioxide when we breathe in. Now, let's imagine that we're thinking now about the out breath. We know, right, that all this gets consumed, doesn't it? We know that that's not going to be there anymore, don't we? Well, let's see if that's actually the case. And I'm being a little bit provocative there. I mean, the answer to that is no, we don't. I mean, it basically isn't. But let's first of all do what we did right at the start. Let's address nitrogen first of all. So we're going to draw our nitrogen in. Now, what do you think? More, less, the same? Now, I'm going to tell you that, and again, I'm just sketching here, so you by all means use, you measure this exactly so the angles are consistent. But I'm going to say, there we go. I'm going to go to my yellow. I'm going to fill that. We have got, once again, 78% of the air we breathe out, just as it was when we breathed it in, is nitrogen. Now, there are some specific circumstances where these numbers would differ. I'm not going to go into these, but if you were to research things like the bends and coming up from deep water or high pressure very rapidly, you might sort of have a bit of an insight. We don't need to worry about that here. Just be aware we're talking about here effectively in normal circumstances. Now here's our really interesting bit then. Well, what is the condition of our oxygen? It's all gone, right? It's all disappeared. It's all being consumed. It's all gone to the mitochondria, right? Wrong. What we find with our oxygen, if I go to about there this time, again, I'm only estimating, you guys can plot this exactly, but if I go to about here, what we find with our oxygen now, let's fill that, is that it now occupies something like 16% of the air we breathe out. So just reflect on that for a second. We are consuming a relatively small proportion of the oxygen which actually enters the lung. The majority of the oxygen that enters our lung is actually breathed out. Were we aware of that? Now, if you think about that from a performance perspective, that would mean that somebody who could consume more of this, so effectively this area kind of got smaller, this person would be much more effective in athletic circumstances. Now, what we're also going to suggest here, I think I used that pink there, we're going to suggest that this part here, and of course there should be another 1%. I haven't actually included it here, but we've now got 4% here, and that 4% is CO2. In other words, one of the products, in fact, let's write this in here. We know, for example, that CO2 is a product. You could even talk about it as a waste product. It's a product of aerobic respiration. So when we breathe out, of course, the quantity of CO2 in the exhaled air is higher, significantly higher, because of course it is a product of aerobic respiration, therefore we need to expel it, get rid of it. But the real big takeaway, apart from the percentages and the shares here, the real big takeaway is this number here, I feel. The point I want to make to you is, okay, we're identifying here that not all oxygen is consumed. So if an athlete can increase that percentage of oxygen which is actually consumed, that would actually make this number smaller. This athlete would be aerobically much more potent or successful. And there's some interesting reflections for you to take away. I'm not going to get into adaptations and how that would actually happen. You might want to go to your biology studies and look at what makes diffusion, for example, efficient at the lung. You'll get into all kinds of stuff, short diffusion pathway, ventilation, a diffusion gradient as well. But the point is, if we can get this difference to be greater, then an athlete will be more aerobically capable. Okay, there we go. Cheers.